TFR. It's a very near institute where I finished my PhD. And the topic of the talk is non-local Calderón problem, and it's an inverse topic in the area of inverse problems. And he actually is an expert of homogenization also, so we are all should be asking all the possible questions after his talk. So Tuhin, you will have, I told you, you will have 50 minutes, 55 minutes, and then last 5 to 10 minutes we'll keep for the comments and all. In the audience, we have students. In the audience, we have professors. We have experts of the inverse problem also. So please feel free to flow as you want.
Yeah. But how to add the slide?
Below there is a symbol of the.
Now, can you see that?
Yes, I can see your whole screen.
Okay. So, how to make the full screen? So fine. Okay. So, but I can't see you. Anyway, so
I cannot see the slide.
Oh, you cannot see the slide?
It means you just shared the folder, I think.
Oh, no. Just a minute. Right now, can you see?
Not yet.
Oh, no. What's the problem? So I'm just opening the PDF, but why it's not working?
Did you open the PDF?
Yes.
Stop sharing and then share only the PDF.
Okay. What do you mean by how to do that?
Do you have a symbol of arrow below in the box? Arrow in the box?
No, I can see the open share tray.
Yes, click that and then there will be options.
The options are like enter screen, window, or
exactly. So click on the window.
Click on the window. Okay.
Then there will be options. What windows are open?
Now it shows. No, previously it was not showing. I mean, the PDF was not showing. Now you can see.
Yeah. Yes. Perfectly all right. Yes.
And
super.
Right now,
excellent.
Right now also with full screen.
Yeah. Yes, with the full screen. Perfect.
Okay. Okay. So thank you very much for inviting me to giving a talk there. I never give a talk in Chile. So only in the Northern Hemisphere. This is the first talk in the Southern Hemisphere. So thank you very much. So without further ado, so let's start. It's late. So I'll be talking about non-local Calderón problem. So so the Calderón problem was posed for the local equations. So I'll introduce what is the relevant or the non-local analog of Calderón problem, what I did. And so it falls under the category of the inverse problems. So the first I will talk about, so what is inverse problem and what is the significance of Calderón problem, and then we'll move into the non-local part. So let's begin. So the overall outline is divided into 3 parts. So first, as I said, the Calderón problem, or in general, the inverse problems. Then it would be on the fractional Laplacians. So there I have some contribution. And then I will be talking about, so what is the way we solve the non-local Calderón problem, or like Calderón problem for fractional Laplacians operator. And that is based on certain approximation properties, so that I will discuss, and will also compare the local and non-local analog, and try to spot the differences as well. Okay, so this is the picture you can see. This is the field map, and here you can see that. So so this is the surface of that the body or like wherever you're measuring. This is the ground surface. So here you have the electrode. So basically it discharges a voltage, and if you discharge a voltage, so it will pass through this medium, and then so these are the current lines, and this will pass to this medium, and then you have the receivers here, and the receiver will receive the current. So you have the voltage and current measurement on the top of the surface. You do not have access to the underground surface or in the medium, like it could be anything. So a priori, you don't know what is the conductivity or the resistivity of that medium. But what you know that on the surface, you can, you know the voltage and the current measurement. So of course, the current will depend on the medium, like depending on the conductivity or the resistivity. So you'll get different measurement for the different voltage. And now based on that measurement that you are doing on the surface, your job is to say that, well, can I predict or can I say what is the conductivity of the medium? And that conductivity of the medium, you are talking about the interior conductivity of that medium. So there you do not have the access. So of course, if you know the conductivity, so if you apply the voltage, then you know the current. But that's the direct problem. Now the inverse problem is that you know voltage and current only over the surface on the boundary. Then you want to figure it out that what is the conductivity or what could be the conductivity in the interior. So that's how the formulation of the inverse problem goes. So this is a very common problem in geophysics, appeared in 1920. Then A.P. Calderón was actually an Argentinian mathematician. So he was working in an oil company, and then before becoming a mathematician in University of Chicago. So he formalized this problem. He could not solve the Calderón problem he posed, but he solved the linearized problem. So though I'll talk about like what is the meaning of this linearized problem, because these kind of inverse problems are highly nonlinear. And he proposed some method for the linearized problem, and later that has been exposed to solve the in general problem. Okay, so let's get into that. So so if you have the class, so if you do not have any, so if you think of the identical medium of the space, then you have this Laplace equations, the Laplace u equals to 0, if you can think of the vacuum. But now I just wanted to formulate in the geometrical way, just to show you a couple of things. So this is the domain or the space you can think of as manifold. It's a compact space, and here is the metric you have. So that represents the medium. So if G is like just the delta Ij, so that means the usual distance function, the metric function, then it goes back to the Laplace equation. So since, as I said, that it depends on the point and also the direction, or as it represents the conductivity or certain properties of the medium. So that's why you have a non-homogeneous G here, and then it will lead to some Laplace-Beltrami operator in M, and that you can also write it down locally as second order PD. And as you can see that, so this is the anisotropic matrix that appears here. So our job is to determine that G. Okay, so now this is the mathematical formulation. So you have Laplace G u equals to 0 in M, and then u equals to F on the boundary. So that the Dirichlet data F actually represents the voltage on the boundary. And then you calculate the flux. So that means once you know F, then you solve U. So then you can, you know that what is del nu U. So del nu U represents the current flux on the boundary. So now you know the voltage, you know the current, and then your job is to figure out what is the G that represents the electrical conductivity. So this you can also formulate in terms of the Dirichlet-Neumann map, as I said. So this is precisely the definition of Dirichlet-Neumann map. You can also figure it out. I mean, you can also pose it via Neumann to Dirichlet map. It's the same. And essentially, you can also think of like taking the Cauchy data. So that would be the graph of that function, lambda G. And the inverse problem is that, so let's say you know the DN map or the Cauchy data on the boundary, then you want to recover G in the M or in omega, like in the PDA. So that's the Calderón problem. And this problem is not solved yet. So I'll talk about what is solved and what is still unsolved. And this problem also highly dependent on the dimension. For instance, that if you pose this problem in one dimension, then it fails. That means that you have only information at 2 points in one dimension, and that is not enough to determine anything in an interval. But in 2 and higher dimension, so in 2 dimensions, this problem is a bit difficult that you can easily understand from one perspective that is known as the dimension count. So you see that, so if n is a domain in Rn, so then your boundary del m would be that n minus 1 dimensional surface. So you lose 1 dimension. So, okay, so you have the Dirichlet data and Neumann data. So that means n minus 1 plus n minus 1. So that is 2n minus 2 variable you have that you know. If you try to think in a discrete setup, and then from that 2n minus 2 variable, you are looking for recovering something that depends on n variables. So naturally, the 2n minus 2 should be greater or equals to n. So then if it is at n equals to 2 dimension, then the 2n minus 2 it becomes equals to n. So that's why, so you have the exact information, and that's why in 2 dimension the problem is difficult. If you go higher dimension, then you enjoy more information, because then 2n minus 2 is strictly greater than n. And so rather, it's a kind of overdetermined situation. So you have more information to recover G. So that's why it was first solved in 3 dimensions, then in later 2 dimension. However, in 3 dimension, the general problem, as I said, if G depends on X, and you have all these directions are open, it depends on the the direction wise. So then in 3 and higher dimension, it is still not known that whether you can solve this problem, that you can solve the Calderón problem. But in 2 dimension, this has been shown that even if it depends on various 2 directions, then it is possible to determine G from the boundary information. Okay. So this is the prototype equation. So this is for the conductivity equation. Then you can also pose the same problem, for instance, like the Schrodinger equation, recovering the potential that I mentioned. Also like the magnetic Schrodinger equation, so recovering the magnetic potential also, that's a vector potential. Then of course the Maxwell equations or the elasticity equations. And so idea is the same. So you have the boundary measurement, and then you want to conclude something in the interior. And these are the problems like heavily used in the applied mathematics, and in a sense that this has application in imaging process. I'll also mention some of them, like in medical imaging. And that one of the things is like EIT, electrical impedance tomography, or it's also known as PAT or TET, photoacoustic tomography or thermoacoustic tomography. And then the equation changes from somehow from electric equation in EIT or the heat equation in thermoacoustic tomography and so on. And also like you have this inverse scattering problem. So like instead of measuring on the boundary, so let's say you are measuring a little far away from the domain, but you do not have the access in the domain. So that's kind of the far field data, and from that, or the scattered data. And the idea is the same, like from the scattering data, you want to see whether you can conclude something here in the interior. So the idea is that if you do not have anything, so if you send a plane wave, so it will pass through. So, but if you have some object here, so if you send some plane wave, it will immediately scatter. And then you measure the scattered wave, and from that scattering data, you try to figure it out the location of that object, or size of that object, or how big it is, or etc. So that's a typical approach, like finding cancer cell or tumor in brain or something like that. And there's also a problem, it's a very interesting problem related to which are known as the geometric problems. So in geophysics or seismology, that I'll also mention. And then the final thing is invisibility cloaking. That's that, as I mentioned, that you you do not have, I mean, you cannot solve in 3 and higher dimension, for instance. Even if you have this anisotropic matrix, like if it depends on the directions, in all possible directions, then you can show that you can't solve the Calderón problem. That means that lambda g does not uniquely determine g. So there is a class of G you can produce by simply producing some diffeomorphism. And the idea of the diffeomorphism is that, so it changes the interior, but it keeps boundary fixed. So if you have such kind of diffeomorphism, then under the diffeomorphism, you don't see any change on the DN map, but on the boundary, however, the G changes in the interior. So, so that means like this is one of the counterexample that you can't produce G uniquely from lambda G. But now the question is that that is the only obstruction. So if you know that is only obstruction, then at least you have the complete idea of so how it differs. But that is also unsolved. It is solved for 2 dimension, but it is not solved for 3 and higher dimension. But I must mention that if you additionally assume that your conductivity is analytic, then probably you can solve it. But under general L infinity or even C infinity data, you don't have this. But then the idea is that then you profit from that. So the profit from that means like, okay, so you can fool someone, or you can hide something, or you can cloak something, that you can via this diffeomorphic changes. So you don't see, since you don't see changes from the boundary, so if you put G1 or G2 under the diffeomorphism, so from that DN map, you can't conclude. And that's the starting point of cloaking, and it has a lot of applications, at least in setup or something that I heard. Okay. So the next thing I'll be talking about the Gelfand problem. So it will be based on, so not on the electromagnetic wave that I mentioned, which satisfies the Calderón, the conductivity equation, which is in the elliptic type. So now I talk about sound wave, so which will be solving the wave equation, so completely a different type of equation. And this is the idea is very common in seismology or like in geophysics. So you have a bunch of sources here, so that produce, these are called geophones, so that produce a sonic boom. And the sound wave, when it passes through different media and different layers, so it has, so the sound speed changes due to the different medium. So it changes, it can go faster, it can be slower, whatever, and then it will come back and that you receive. And that from that information, from the scattered wave, sound wave, you try to predict that whether there is oil or is there any material or whatever. And you also try to predict what is the depth or what is how much it is and so on and so forth. So this is also known as the Gelfand problem, so as he proposed. He proposed in 1 dimension, and then later it was been introduced in higher dimensions. So as I said, so this is your wave equation now instead of conductivity equation. So you are in a cylinder. So this is the base space and this is the time space. And so so you do not have, let's say you have 0 initial data or 0 initial speed. So that's not the problem. So now you have the boundary data on the cylinder, so on the surface of the cylinder F. And then you are measuring this Neumann data, that flux, on the boundary. And from this two information on the boundary, you try to predict what is the sound speed or what is the metric G. This depends on the sound speed. So that's the problem. And so this is like lambda G hyperbolic. So because of these hyperbolic equations. And in this case, you can solve this problem. You have a perfect solutions. Not like the elliptic case. And there are 2 methods. One of the method is known as the very famous, is known as the Belishev boundary control method. And the idea is that for the wave equation, you have the advantage of shooting the real characteristic solutions or the real geometric optic solutions. So idea is that through the real characteristic, so you can start from the boundary and go inside via the characteristic. I mean, if the maximal characteristic go all the way up to this, then you have full information. If it goes up to this, okay, so that means you can get at least step by step this information. Then you go a little more inside and then proceed further and try to get the whole information about G. But such idea will not work for the elliptic problem, because there you have the complex characteristics and it doesn't work in the real problem. But it works at least for the hyperbolic equations. And if you measure for the enough time, then you can cover the whole surface. I mean, that means the whole M. That's the way you do. So, and there is also something called that, as I mentioned, the real geometric solutions are called the Gaussian beam solutions. So that you send a beam of waves, and from that you can locally determine the it's called the quasi-mode of this G, and then step by step you do. So what I'm trying to say that the problems are quite different from the elliptic setup to the wave setup, and here you profit actually in the wave setup. You can actually solve this problem in any dimension with any G. You have a lot of applications, and for example, one of the common applications, that's the ultrasound tomography that uses for that pregnant women. I mean, you can do it for any soft tissue or like where you have fluid, and using the sound wave and the time reversibility of the wave equation, you can image what is going on in the interior. But as you can see that you do not have the access in the interior, but still you can draw the image what's going on in the interior. Okay. So now, so still, these are the two models I explained. That's about the local equations. Now I'm talking about something. We're talking about some non-local equations. Okay, so this is the third case. That's the X-ray transform problems, and this is the X-ray machine. And we have like more or less we all know that about these X-ray machines, or like it's called this CT scan, there's computerized tomography and stuff like that. So the idea is that so this is for the heart tissues, like so you do not have the access to the interior. I cannot open your skull and see whether you have a tumor inside your brain or not. But I come up with a method that will be enough to determine, or I can image your brain, and then that will be enough to say that whether you have a normal cell or cancer cell or tumor or whatever. And the idea is very unique in a sense that, so basically, it depends on this problem that, so let's say here there is a function f in 2 dimension on this disk. You don't know that function. What you know that if you send a if you just shoot a line, a ray. So this is the straight line joining 2 points on the circle. And if you integrate the function over the straight line, that value you know. And now you have the access to choose whatever line you want to choose. So like it could be this, that, whatever the straight line you want to choose. So for all possible straight line, you know the integration of that function. Now, can you tell me what is that function? And yes, you can. You can recover uniquely that particular function from its integral over the straight line. Now, remember that function is defined, it depends on 2 dimensions, but the integration you are doing on the straight line, which is just a 1-dimensional object. So that is also known as the Radon transform. So though Radon introduced the transform for 3-dimensional case, and his idea was that in 3 dimension, you do the integration over the 2-dimensional plane, and you ask the same questions that whether you can do it or not. And if you reduce it into the 2 and 1 dimension, so then it becomes, as I mentioned, it's also known as the X-ray transform in what the straight line case. So if you change the medium, so let's say or change the metric, so then of course, as you can expect, the straight lines will be replaced by the geodesics. That means the shortest distance between these 2 points. And in the complex case, this has been also studied. That is known as the Roger Penrose, the Penrose tomography, or the Penrose problem. At the same thing. So in the setup will be everything in the complex Okay, so as I mentioned that if you think of like geophysics, that where you do not have the same material, so so you have layers of different material, mud, rock, water, whatever, and so that means like if you think of, so then it's due to this inhomogeneity, so you have to think of like the geodesic. And so let's say this gamma represents the geodesic, and then the same problem. So you integrate that function over the geodesic, and that information you have, and from that information you want to recover F. So the point is that now if you think of this I, that operator, the symbol of this operator is actually a non-local operator. So, or this, it's a zero differential operator. But it doesn't have proper support. It's actually a non-local operator. I'll talk about later. But the major difference that I want to spot that, as I mentioned, that in this equation, or like the previous equation, but Laplace equation, so these are the local operators. And here in this, or the symbol is local. Here you do get one symbol, which is not only zero differential, but also like it's a non-local. So that means it does not preserve the support. Okay, and the second one, or the last one, before introducing the fraction problem, so that it's known as the scattering relations, as I mentioned. So so the idea is that, so you shoot some ray, so start with a point with a direction, and if your domain is inhomogeneous, so then of course it will pass. I mean, when it will exit, so you'll get a different point, and more importantly, a different direction. So now let's say you know this and you know this. So because you are sitting on the boundary, you do not have the access in the interior. Now from these two informations, it's also known as the scattering relations to the lens relations, that this xv and x theta v theta, let's say. Can you say what is the medium, or what is the metric, or whatever the quantity it represents, the inhomogeneity in the medium? So these are the typical inverse problems we study, and here also that so this is solved in 2-dimension case, but still this kind of problems are unsolved in 3 and higher dimensions. So I just wanted to mention that these problems are very much dimension sensitive, and stability depends on dimensions, so on and so forth. That's also one of the reasons that you get the CT scan as a 2-dimensional image, not the 3D image. Okay, so now I'll briefly go through that the first problem, the Calderón problem, where at least it is known or solved. Okay, so if you assume that your metric is isotropic, that means it does not depend on the direction. It's just it's a scalar function gamma x. Like every direction, it's just the same function gamma x, which is a positive scalar function representing the electrical conductivity. Then in that case, you can uniquely determine gamma. And one of the way it has been done, that you can reduce this problem into a Schrodinger equations, where you can write it down the potential Q via gamma like this, with this change of variable. And so now you have minus Laplace plus Q. But then your DN map also change from lambda gamma to lambda Q. But then first you have to show, or you can show that you can, from lambda gamma, you can recover lambda Q. And then from lambda Q, you can recover Q. It's just works as the perturbation of Laplace operator, which doesn't work if you work for the anisotropic matrix, which depends on various directions. So that's a case here, at least, that you end up with having one particular scalar functions. And then I'll mention about what is the method they use to find Q. But as a result, what I'm saying, that you can recover Q from lambda Q on the boundary. And of course, I mean, the sign of Q doesn't matter, like it will be positive, negative, just a infinity. Okay, so this was first solved in 1987 by Sylvester and Uhlmann in 3 and higher dimension. As I mentioned, this was the first case. And because here you enjoy more information, and then it has been reduced into ln by 2 class by Shanilo and other people. And of course, from the practical purpose, that you don't want to work with like very lower potentials. I mean, you assume that in practical case, all your you are in a smooth setup, but there is mathematical interest that and it is the following. So if you consider this equation and if you ask the unique continuation principle, or the UCP in short, so that means like if U is 0 in UCP says that you have this it's with the infinite speed of propagation. So that means if U is 0 here, let's say in a subdomain of omega, then U is 0 everywhere, right? So that's a unique continuation. You can also say that if U is small inside of any subdomain of omega, then U has to be small in everywhere in omega. So that works for the elliptic equations where you have the complex characteristic. That's not true for the wave equations or where you have the real characteristic, because the information the singularity can go through via real characteristic. That's not true for those kind of operator. At least here you have. So now in the unique continuation problem, that if you have a potential just ln by 2 minus epsilon, then it fails. So like you do not have unique continuation. So this is the optimal class you can find solving the unique continuation problem. Now what they have found that somehow this inverse problem, which is apparently no connection with the unique continuation because inverse problem was given from the boundary, but somehow it is connected to this unique continuation, at least when you consider the right class. So, however, it still is an open conjecture. It is not proved that if you go for ln by 2 minus epsilon, let's say, for that potential, that you can't determine q from lambda q. That is still not known. What is known that at least for this right class where this unique continuation holds, you can solve the inverse problem. And for 2 dimensions, so it was solved quite recently in 2008 and 2015 with this relevant classes. Okay, so now I want to introduce one more problem that's also known as the local data problem. So it's quite simple to motivate you that the problem is that if the domain is quite big, so then you do not have access to the full boundary. So you have the partial access to the boundary, let's say this red portion, and the question remains same. So let's say you're prescribing the voltage here, you're measuring the current here in this part, and then is it enough to determine the conductivity or let's say inhomogeneity or the obstacle inside the domain? And this is the black part that represents. So this is known as the local data problem. And that particular problem is solved in 2 dimensions in 2010, but it's not solved or it's still open in n greater or equals to 3. The known thing is that if you further assume certain boundary conditions on the inaccessible part, like this part, like if it's a part of a sphere or it's flat or something like that or cylindrical, like where you can do all sorts of reflection idea or like Kelvin transform stuff like that, then probably you can. Otherwise, still it's not known. And the idea, as you can imagine, that if you want to flat the domain near the curved surface, then immediately we end up with having an anisotropic matrix here. And as I said, that in n greater or equals to 3 dimensions, that anisotropic problem is still open. So we don't know what to do. So that's the problem. Okay. Now with this, I will introduce the non-local or the Calderón problem or the Calderón problem for the fractional Laplacian operator. So let's introduce what is fractional Laplacian operator. So as you know, so the symbol of this operator is mod c to the power 2s in whole Rn. So you can define it via Fourier transform. The Fourier transform of this is mod c to the power 2s into u hat. And if you do the similar Fourier transform, you get back to the physical space. The main point is that this kind of operator are non-local. So that means that it does not preserve the support. If you have s equals to 1, like Laplace u, so then you know that if u is supported, if u is a CC infinity function, then Laplace u has a support in the same support as u. But if you do the same thing for minus a plus su, where s is not an integer, so then it is non-zero everywhere. in fact, we'll show later, and it's a very different thing, like unique continuation principle that will prove for the fractional Laplacian that if u and minus a plus u are both a 0 in certain open set, then u has to be 0 everywhere. I mean, everywhere means in whole Rn, because as you can see that if as you have defined through Fourier transform, so you have been were asked to define it through whole over Rn. You can't escape it. So yeah, so it's a kind of, so this is a non-local or anti-locality it enjoys, and we'll show that. So that has a lot of advantage while you're solving the inverse problem. So it carries more information somehow, and so it helps to recover the potentials or the conductivity and stuff like that. Okay, so so where this fractional Laplacian appears, so these are some equations that I'm going to talk about. So mainly in studying the different diffusion model. So if you think of Brownian motion, so the idea of Brownian motion is that, so you have a bunch of particles suspended in some fluid or in some gas, let's say, and then you want to find the probability density function that where you can expect to find most of the particles, because particles are jumping inside the fluid, and that probability density function that satisfies the normal diffusion equations or the heat equation. Now, if you think of this the super diffusion model, so then it satisfies the fractional heat equations. Now, with respect to this, the fractional means that the fractional derivative is coming with respect to the space variable, and it's contributed to the Levy flight. So that means that if you have a probability distribution, so like if it has a long tail, so like it goes very slowly to 0. So in fact, so here you know that the heat kernel that has that exponential behavior when it goes to 0. If you study the heat kernel here, it has a polynomial behavior. So so that's very much different. And if you want to study the subdiffusion, so then the derivative, it's on the time, and it's also known as the Caputo derivative, because as you can see, that time is like here t is greater than 0, not like x here, like it goes in both directions. It's also known as the Caputo derivative, and it's also attributed to that it's known as continuous time random walk. And the idea of having this alpha here, so that means you allow the particle to wait or halt to make the next jump. Like here, that's the whole idea of having this alpha, to study those kind of model. And it can jump in a long range and also in a short range, and depending on the problem. So as far as I can understand that if you want to study some medium where the particle or the particles allowed to be jumping from one point to another point, you can of course give certain conditions like having membrane or stuff like that to control the jump process also, or to kill the particle when it exits certain membrane. So that you can do, but the point is that you want to allow the jumping like between any 2 points inside the domain. So then the fractional Laplacian is the right thing to study, or the right thing to model that particular problems. Okay, so with this, so we are going to study the static case, or if you take the certain Laplace transformations, then you will reduce to this kind of problem. And so this is our fractional Schrodinger equations. As you can see that now you have the fractional Laplacian operator instead of Laplacian operator that I talked about, and minus a plus s plus q equals to 0 in omega. And instead of the boundary data, now we have the exterior data. And as I mentioned that since this operator is a non-local operator, so then you have to give value throughout the whole domain. It's not locally defined. So that's why the data in omega e, it is well defined. And with respect to that, we solve this problem. And then we define, this is our DN map. So that's also defined in the exterior domain. So I just want to mention, okay, so from this information about this lambda q, of course, the goal is to recover q, which is defined in omega. I just want to give you one perspective that, so this is my non-local Neumann derivative, as you can see. This is defined in omega e. So omega e represents the exterior domains, Rn minus omega bar. And so this is the kind of integral you have in the physical space. And this has no singularity, as you can see that x is in omega e and y is in omega. So it's okay, fine. And the idea is that if this is the right quantity, in a sense that if you take that s tends to 1 limit of this quantity, it goes, this integral is happening in omega e, but it falls on the, it collapses into this on the integral over del omega with del u del mu. So, and that was our flux in the local case on the boundary. So you can think of like this is the non-local Neumann theta, which represents the new exterior measurement in the non-local problem. So with this non-local Cauchy data, we want to recover Q in omega. And so this is our first result that yes, you can. And if if let's say you have two different Q1 and Q2, if the non-local Cauchy data they are same, then you can prove Q1 equals to Q2. We actually show that you can prove that local data problem that I mentioned, that you have the partial access to the boundary. Now, in this case, the partial access to the exterior data, like it is impossible to measure in a whole Rn minus omega. Like if you can't measure in a small set omega, then it would be great. And we found that it is possible for any W. It doesn't matter how small, how big, how close, how far, it's still okay. I mean, you can do it. And the second thing is that it works for all dimension. So it's not even dimension sensitive that I mentioned several times for s equals to 1 case. And also the mechanism for this is quite different from the local case. So the bottom line is that it's a very different. If you change from just s equals to 1 to s, then you enjoy a lot of things which you can't prove or even can't expect to have in the local case. Okay, so now we'll talk about the last part, that how we solve the problem, and that's the sum approximation theory. So let's begin with the Runge approximations. So that is known in the PD setup, or mostly in the elliptic PD setup. So this is the classical Runge approximation you have, that if you have an analytic function in complex plane, or which satisfies a D-bar equation in complex plane, then you know that you can approximate such functions via the complex polynomials. Now, for the elliptic PD, it's attributed to Lax and Lagrange. It says that, okay, so let's say you have a PD in omega, and you have a PD in a subdomain U, and elliptic PD. And then the idea is that the solution in U can be approximated by the solution of omega. Now, the catch is that when you are studying the PD in omega, so you can give any boundary condition, like let's say Dirichlet boundary condition. But when you are studying the PD in U, that you can give another boundary condition, let's say Neumann boundary condition, Robin boundary condition, anything. So it's not, so the point is that it takes care of the interior and it's reluctant to take care of the boundary. So that's the flexibility you have. So you can approximate the solution in U by the suitable solution in omega, and that too you can do with the partial data. So let's say you want to study, you want to consider a sequence in omega such that in this part it is 0. I mean, this part means like this boundary it's 0, and it's supported only here. That's also fine. You can do it. So that's the Runge property for the elliptic PD. And so one of the application is that this is a precise thing I was trying to say. So let's say gamma is the local boundary. So here you have the source, rest of the black part on the boundary you have C. Then you can subdivide this domain into two parts, let's say U0 and U1, and you can construct a sequence of solutions solving an elliptic problem where in U0 it goes to 0, where in U1 it goes to 1. I was told that is kind of the idea for the, and the same thing we can do for the Maxwell equations, and that's the kind of idea that without having a charging station, you can charge your mobile. So the idea is that you can localize the electromagnetic wave, or the charge or the energy in one particular domain. As you can see that the solution restricted in U1 can go to 0, but in U0 it goes to 0. It has been also used in a I mean, from this nature, as you can see that it immediately solves the kind of problem with a high contrast method, we say, in a sense that, of course, I mean, if you have the object here, I mean, U0 U1 is like you can change. So if you, let's say you have the obstacle here, so then immediately you can spot by this measurement, because like you'll get a high contrast, like this is almost white and this would be like black. But the problem is that it will have very low resolution, and the reason is that between U0 and U1 you have to give little bit space where you do not have controls. That's that I mentioned here, and that's why here the picture will be very blurred. So low resolutions but the high contrast. So that's the effectiveness of the of such imaging method determined by the elliptic PD. And this has been used like many people, and you can do it. And this Ikehata and stuff of that master on this to finding the the obstacles here and what is the location size and everything. So, but also you can see that this part is also attached to the boundaries. So, and as I mentioned there, you do not have access to that. So now, in order to solve the problem, where you're, since you do not, I mean, you want to get, if you don't know here your gamma, so then you're lost, because you don't know how to do it, because here you do not have any access, right, in this method. So then that the method what was introduced, that is known as the complex geometric optics method, and the complex geometric optics method that takes care of that part, that it allows to determine conductivities that can oscillate near the del omega. So that means like it can oscillate near here or anywhere, doesn't matter. You can still figure it out what is there. And for that, so like the real geometric optics solution, as I mentioned for the wave equation, so you produce complex geometric optics solutions for the elliptic equation in Cn, and then you reduce into Rn. And the idea is that this is the part will solve the that harmonic oscillation. This is the part will solve the harmonic equations, or these are the harmonic functions. And then you have this R, the extra term, that will take care of the potential that Q. And if you choose a high amplitude like rho tends to infinity, you can prove such estimate that the error term goes to 0. So by that, and since it's in Cn, so basically you recover the Fourier transform of that unknown constant or coefficient or the potential, and so basically you recover the Fourier mode, and then you come back to the physical mode. So first you recover the Fourier transform, then you recover the function. So that's why it's a two-step process, and the disadvantage of having that, it loses the stability. So if you make mistake or like if there is an error, so then while recovering the function, then the error is amplified. So that's the problem. Okay, now let's talk about what is the idea in the fractional case. So in the fractional Laplacian, so we have this strong uniqueness property that I was just mentioning before, that you take any distribution, it doesn't matter with the regularity, and then if u and minus or plus u both are 0 in some non-empty open set, then you can prove u is 0 everywhere in Rn. And certainly this result is not true if you put s equals to 1, because you take any CC infinity function, and outside that support, u and Laplace u both are 0. But from that information, you can't say anything about u. You still could be non-zero. But here, outside the support of u, if this is 0, then both are 0 in whole Rn. It's identically 0 function. And let me quickly go through the proof. The idea of this proof is related to this Caffarelli-Sylvester extension. There is also another proof we found by the heat equation. That's a different issue. This was the first proof we gave. That's by the Caffarelli-Sylvester extension. And it says that, sorry, it says that if you consider this degenerate elliptic equation, so as you can see that the degeneracy is here as s is greater than half or less than half, that y goes to 0, it can go to infinity or it can go to 0. For s equals to half, you get back the Laplace equation. And then you have at the Dirichlet data, you have the function u. Then if you compute the Neumann data, then of this PD, then you get back the fractional Laplacian operator. So now it goes back to this question that let's say you have a harmonic functions, and if u and del nu u both are 0 on the same part of the boundary, so then you know that u is 0, right? So that is the thing, that's the exercise, the Gilbert-Turing, that's the exercise you want to do for the degenerate elliptic equations, and that we did. And then you can apply, so then you can, so first you prove that near y equals to 0, it is 0. So then you can apply, then you can lift a little bit from the 0. So there you do not have any problem, no degeneracy. And then you can apply the Sarbander's theorem, because like this is analytic away from the 0, so it will be 0 everywhere. Again, the idea of invariant speed of propagation, and that gives you that this result is, which is not true for the Laplace equation. Okay, and having this result, now we have this kind of Runge approximations that if you solve that fractional Laplacian equations, then the solutions are dense in L2 functions. Like we are not saying that it is dense in another class of elliptic solutions. No, we are saying that you take any L2 function, any, then we can approximate that function with respect to the solution, which is solving the fractional equation or the fractional Schrodinger equations, whatever. You can put q equals to 0 as well in omega, and u has support in omega and w. So that means if you go back to this picture one more time, so u is non-zero here, u is non-zero here, and u is 0 everywhere. So that's the source in w. And that we can do. So this can be done in L2 or in Salo spaces. So, and then if you want to do it in the smooth spaces, then the right quantity, you have to divide u by the distance function dx to the power minus s. Because unlike the local equations, so if you have the smooth data on the right hand side, then u is not necessarily smooth. So it's like u divided by the distance function is smooth. And that that you can, if you consider that right quantity, then you can show that for any given function in CK, you can produce a sequence that approximates this, and you solve this equation. And this was also appeared in the work of Savin and Valdenush and Dipler, but they do not have control, as I mentioned, the W, our support lies on in omega and W. They do not have that. So they are considering in the whole exterior domain, like Rn minus omega. But it's true that they also have similar results beyond bar. And the point is that if you put s equals to 1, you cannot expect such results, right? Because you know that harmonic functions, if you consider the harmonic functions, you take limit of the harmonic function, you end up with having another harmonic function. And so no way you can approximate L2 functions. So they are like nowhere dense functions. But just change from S to 1, you have such a nice approximation problem. Okay, and so that was the main ingredient to solve our problem. And so later we also found that even if I have the equality or the information for one single f, so that's a single measurement, you can have you can recover the potential q in omega. You can provide a formula for q from this lambda qf, and just from a single measurement, you can also prove the stability for from a single measurement, and that's the work of Uhlmann. Later she did. And the point is that such kind of result, again, you can't expect to do in the local case. As I mentioned that about that recovering the Fourier transform. So that means you need to know that all possible Fourier mode, then to conclude that you know the functions. The all possible Fourier mode means that you have to vary the functions, like you have to vary the rho. And that means that you are varying all possible functions. So here, just with one measurement, one function, you can do it. So that's how it's this result is drawn. Okay, so having said that, this is my final slide. So this is an anisotropic Calderón problem. So there I introduced that minus divergence x grad operator. So like this is a generalized elliptic operator, as you can say, or like if you go back to the first slide, just wanted to show, sorry, maybe I forgot. It's like this. So sorry, anisotropic, not like the Laplacians, but now you can consider the anisotropic case. And in this case, for s less than 1, you can solve this problem again from a single measurement. That means you can recover Q from the exterior data. And again, that's not known or unsolved in the local case. That means s equals to 1. And we do not know how to solve it. That's also the problem. So with this, I stop here. Thank you for your attention. I hope I didn't take too much time.
Thank you so much, Tuhin. It was a fantastic talk. I have lots of comments, but let's first ask the others if they have something to say. Yeah, please go ahead. And if you have any comments and any questions, anything, please go ahead.
Yeah, as Ravi said, it was very nice, the talk. I just have maybe one question for the moment, but maybe there are lots of questions to think about. So, so in these kind of inverse problems, the beginning you started with Neumann data on the whole boundary or part of the boundary. So probably in applications it makes more sense to just have if a finite number of points where to make measurements. So
Absolutely.
what
finite
can you
number,
say?
finite number of points, like that will be 0th dimension.
Yeah, so
but
that's the
what,
difficulty.
yeah,
Then you, I mean, you can do, but that would not be helpful to conclude anything.
yeah.
Even I must say that here you can see the slide, right?
Mm-hmm.
You can, right?
Yeah, I can.
Yeah,
Okay.
yeah.
I was just confused with this. I never use this setup actually. This is not Zoom, right? So so in the local data problem, so now, so I didn't mention that, but I should have mentioned that even in this red zone, depending on the dimension, in n equals to 2, it's like you can take any gamma, like it doesn't really matter what size. Like this is an open set, one dimensional, but it's, of course, it's non-empty. Its measure is surface measure is strictly greater than 0, so that does not allow your point thing. But the size could be arbitrary, and still you can do it in 2 dimensions. But if you are studying the 3 dimension, then you have to consider almost half. Like it should go all the way this, and it should go all the way this. Like the point is that it's in fact you have to consider that's more than half. Okay, and then only you can do it. Of course, you can form the question with the very little measurement, but those things are not known yet. So, in fact, like if let's make the problem a little bit easier. Let's say you want to know just only here in the neighborhood of gamma. Forget about this part. Then also you don't know, and you don't know what is the method you should try. That's also a problem.
Mm-hmm.
So what we did, it means me and Andrea, you know Rajesh Andrea, right? So
Yeah.
we know that the inverse problem does not have any explicit answer from the mathematical point of view. So what we did, we convert the inverse problem into the optimization problem, and then we found approximate solutions, and the numerics, at least numerics point of view, they're giving excellent results. Yeah.
Mm-hmm. And
Yeah.
one more question. So Tuhin, you said that, meaning when if the dimension this dimension condition, so if the dimension is higher, you have more information, and so you should get better results. Or be able to determine. But many of the results which you like later gave us were more complete answers when the dimension is 2, and in higher dimensions.
For example, here, yes,
So,
that's
yeah,
true.
yeah,
This paper is very complicated actually. But
yeah.
this is true that in two dimension, actually in two dimension, the intercalculant problem is solved. Because the idea is there that you can, what they do. So okay, so you can think of the Laplace operator as a d bar operator in two dimensions. So you study the problem in complex plane, and there you have a lot of results that you do not have in 3 and higher dimensions. So and there was a series of work that started by actually Vasif Ibrahim and Kari Astana, so if I'm not mistaken. So you can see that in the original Calderón problem that was first solved in 3 and higher dimension in 1987, then it took almost 2008 to solve in the two-dimension case. However, later, then it has been shown that all other problems, especially related to, though I'm not giving you the right history, there are back and forth things, like different methods. But one thing I can tell you, the complex method, the complex analysis method, particularly in two dimension, is very successful to solve those kind of problems, which is not successful in 3 and higher dimensions. That's the thing I can.
Okay. Thank you.
Okay. Anybody else? No. Okay. So there are a couple of things which I want to tell you. Yeah. I just sent you a link to him to check out the work what we did with Luisa. Luisa left the room, so she's not here. With
So
Antonello. In the Facebook, I sent you a link.
Oh,
that's
okay.
That's the non-linear problem. Okay, and we defined we defined a new DTN operator, and then we use the DTN operator for the monotonicity. So what you mentioned that Harak was the first guy to introduce the monotonicity. That I don't agree with, because it's 2008, right?
Yeah, you're right. Yeah.
Yeah, but the guy, one of the
actually, I wanted to talk about that. Actually, you raised a good point. Here, I wanted to, I changed the slide. So, okay, according to there is one interesting problem about this. Like if you consider the S equals to 1 case, that the local case, so then again that monotonicity is in the one side. But if you consider S is strictly less than 1, then you can say the monotonicity on both sides. In a sense, let's say you can ask the question in the following way. So let's say your Q1 is greater than Q2. Can I say lambda Q1 is greater than lambda Q2? Or let's start with this question. Lambda Q1 is greater than lambda Q2. Can I say Q1 is greater than Q2 or not? Now,
yeah, so for that,
ways, you can do it S is strictly less than 1 in this kind of thing. And which is not true for S equals to 1 case, but it's true that Bastian Harak is he's from University of Frankfurt. He did this. He has a lot of work there.
He has done this. He has done this. That I agree with you. But monotonicity, to use that monotonicity for the dealing the inverse problem was first done by 2002. In the link which I sent you of the paper, if you can see in the reference, there are some references of this Antonello, who is one of the co-author. They did something. Yeah, they did something much before than the group of Harak, and the converse part, as you said, it's correctly all right that they did for the converse part, but the direct part was done much before.
I see. I was not aware of that. Okay. I mean, I didn't work in the monotonicity part, but he worked into this. One of my Uhlmann. So he did a couple of works in monotonicity direction with Bastian Harak.
Correct. Yeah, that I agree with you. So there are a couple of things which I wanted to, let me summarize what I said just in last 5 minutes. That number one, that for the nonlinear, I don't know about how this operator is connected with the completely nonlinear case, which I sent you the link. Have a look of it, please. And then I would love to see your opinion about it. Okay. Number one. Number two is the monotonicity, use of monotonicity. And the number three, which I want to ask you, what happened to that wave problem, which you said the DTN for the wave problem and parabolic problem? Any result available or something?
Oh, I mean, in the fractional setup?
Any setup is welcome, even for the simple non-linear parabolic equation or hyperbolic equation.
Yeah, I mean, this has been also studied. I mean, for instance, like actually this Gelfand problem that I mentioned for the wave equation, that is solved before the elliptic setup, the Calderón problem. So you have this thing that boundary control method is actually based on the idea that the domain of dependency or the domain of influence that you study for the wave equations, that cone, the double cone you define by the characteristics. So and for that kind of thing, like you can apply the characteristic method, you can apply the real geometric optic solutions or the Gaussian ring solutions. So those are quite successful in the in the wave equations. Of course, there are questions which are quite hard in the wave equations and still it's not solved. For example, it's like you want to determine not only the speed but also the initial displacement or the initial speed. It's like a combination of both and something like that. So those kind of problems are still open. But at least the conventional problem, like recovering the G, it's actually solved not only for the wave equation. Later, it has been studied for the operator with real principal symbol. You generalize into that, and that has been done. And yeah, so that for the for the heat equations, then heat equation is like again it goes back to the elliptic setup. Like you can take the Laplace transform and so on and so forth, and you can reduce into problem like the elliptic case, but also like independently those kind of problems are studied, because if your potential also depends on time and stuff like that. And fractional wave, fractional heat are also done if you think in terms of the evolution equations. Yes, those has been done, but again, I mean, those results are not that much difficult in some sense, because again, this theorem helps a lot because the principal part is kind of controlled. Yeah, but then there's also work by Uhlmann in the fractional wave equations, I can say, if you're asking for that. It's because somehow that kind of operator appears in the pedidynamics. And yeah, and there he also did this kind of thing, like stability reconstructions and everything. So in short, yes, this has been. I mean, actually, this like EIT, as I mentioned, that which is use elliptic equations. That's one of the things that is used for the high contrast method, not for the good resolution. So, but rather, there are other models which are very popular, like the thermoacoustic tomography or the photoacoustic tomography, and those uses more on this kind of parts, like the if you have a heat source, then it will be immediately everywhere you have this infinite speed of propagation of heat, right? So it will diffuse, and then from that information, can you talk about what kind of medium you have? So those kind of problems much more studied and practically useful.
Yeah, I will be really grateful if you send me the link of these references.
I mean, there are books actually, so maybe you can. Okay, I'll do that.
Just in a mail, please summarize the links.
Yeah,
the
so
books and the articles
maybe you can look into this guy Isakov. His name is Viktor Isakov. He
has a very nice book on this. Actually,
yes, in that book you can find on parabolic equations that you asked for, and also I can give you another name. Imamoto. I don't know where is Imamoto is written. Let me show you. Just a minute. So
Yeah,
this
here. It was, yeah, okay.
Yeah, Imamoto has written a book on the wave equation. He has also written a book on parabolic equation. So I would say that that book is great source of doing all kind of research. Like
Yeah, okay, nice, perfect.
so he's
Awesome.
from
Yeah, so
University.
yeah, if you have the link of the book, and please send me.
Yeah,
that.
okay, then I'll send it to you.
In one mail, please include all those links, and that will be great help, because now we are looking for to define DTN for a time evolution problem. Okay.
Thank you.
So so that's all from my side. Anybody else wants to say something quickly, because we are late? Sorry.
Maybe one last comment. So this transformation you made to change the coefficient to potential, it can only work when the coefficient is smooth, right? Or can it work when they are not smooth?
I mean, yeah, you need like W1 infinity. I mean, that's one way. Of course, you can think of like, okay, I can tell you one simple change. Like if you apply the derivative here, so then you get, okay, so the one derivative will go here, so gamma x Laplace. And the second term will be grad gamma grad u. So if you divide by the gamma, so then you have Laplace u plus the grad of log gamma grad u. So here, this kind of transformation give you the zeroth order term, but if you but it uses a Laplacian. So okay, so you can say that you need 2 times derivative, but also you can make it little flexible, like weak sense. But you can also think of having first order perturbation with the Laplace operator, and there you can just simply apply the grad here and then divide by gamma, because gamma is a non-zero positive function. So then you can have a first order perturbation, and then again you can still study the same problem. So and same that's also done. I mean, done in a sense like if you want to study that magnetic Schrodinger equations, so then you have first order and then zeroth order, 2 terms. So here I just give one example with the zeroth order and how this method helps to unfree the inhomogeneity in the leading order operator, just to make it homogeneous. So yes, but there are the optimal results are known for, as I mentioned, like that unique continuation. So here in that case, gamma, if it is in W1n, not even 1 infinity, W1n, then it is known that you can solve it.
Okay.
So, yeah.
Okay.
I mean, your Q may not be in infinity; it will be in different space. But then you try to come up with some new Calderón estimate and try to solve it. That's the idea, actually.
Yeah. Thank you.
Okay, so fantastic talk. I really appreciate your time.
Okay.
Thank you
very
so much.
So,
see you.
So see you in the next talks. Yeah.
Bye-bye.
Have a good night. Bye bye.